sensing system started a little late turning over. So Jin, over to him.
Okay, thank you. Yeah, thank you for coming in such a early time of the morning. I'm Lu Chao from the Hong Kong Polytechnic University. Okay. So what I'm going to talk about today is the integrated communication and distributed sensing system. Okay. I think I've been attending this very great conference. I think most of the work presented here are mostly science. I think what I'm going to present it here are more like it's application of science, okay, physics, mathematics, and see how they can be used to solve some of the practical problems. I think quite a lot of you probably know Chao, and who got his Nobel Prize in 2009 for his work on optical fiber. Okay, I think when I teach a subject of optical communication, I typically ask my undergraduate students to read the paper, because the paper is a very comprehensive study of what we can use to construct a medium for communication. Okay, so I think before that optical fiber, I think people typically use a copper wire for communication. Later, people have tried to study the use of copper waveguide. Okay, I think that's in the 60s. Okay, but the main problem is that the attenuation for such a communication medium is very high. Okay, and then clearly people realize that we can use light for communication. Okay, but the free space light propagation will be affected by many things. Okay? I think if you have bad weather, if you have dust, and because the optical fiber is also, optics is also a line side propagation, so you will have a problem. Okay, but we know that glass is transparent to light. Okay, but if you have like a window, I think the light can go through. But if you increase the thickness of glass, then obviously the light can no longer be transparent anymore. Okay, so then I think people actually have been using this the fiber structure for like endoscope and other things before, but then people thought we cannot use it for guiding light over long distance. Okay, the main thing is that we have a huge attenuation. Okay, I think Chao, what his main contribution that he studied different kind of material, okay, from polymer for the normal glass. Then he eventually realized that we can use pure silicon. Okay, if we make the silica pure enough, we get rid of everything, then it will be a very low attenuation transmission medium. Okay, and he also analyzed the normal scattering inside the glass, silica glass, will not be the limiting factor. Okay, and he made the experimental test. Okay, so he built the system to test the attenuation. Okay, because in order to compete with the copper wire, you need to have attenuation of less than 20 dB per kilometer. So that means at least you need 1% of the power after propagating inside the glass for 1 kilometer. Okay. And but he couldn't produce, because silica, the main problem is that you need a very high temperature to melt it. So it's about 1,900 degrees. Not many people can handle it. Okay. But he got hold of like a 20 centimeter of silica slab. Okay. Then in order to prove that 20 centimeter, we can prove that if we increase to 1 kilometer, then the attenuation, we still can get 1% of light. We actually design equipment to test it, okay, and implement it. So eventually prove to people that optical fiber can be used for communication. So that actually got him a Nobel Prize. Okay. So why optical fiber is important? Okay. So nowadays we have internet. Okay. We can do AI and everything, but the connection among everything, we are using optical fiber. Even like nowadays we are all addicted to mobile phone. Okay. For mobile phone, in order for mobile phone to operate, we owe the so-called base station, because when we use a mobile phone to make a phone call, we are communicating with the base station near us. Okay. But in order to connect all the base stations, then we need the optical fiber. Okay, because the optical fiber have a huge bandwidth, have a very low attenuation. Okay. Then other things, I think, let's say if we do a Google search, so we try to do like use the ChatGPT, everything. We typically connecting to a data center. Okay. But if you look at the data center, you can see that they are all connected with a huge amount of optical fiber. Okay. So that's why with the increase of this AI, the sale of the so-called pluggable optical fiber module actually increased significantly in the past 1 or 2 years. Okay, so all due to this. So why it's useful? Because if we compare, okay, so in wireless path, the typical loss of let's say 10 meter is about 40 to 50 dB. Okay, so that means you have only a very, very small amount of power left after propagating about 10 meter. Okay. But if you compare with the optical fiber, so 1 kilometer, you only lose about 5%. So you still have 95% of the power. Okay. Another thing is that is immune to electromagnetic interference, and that have a huge amount of bandwidth. Okay, because bandwidth is essential for it to support like the communication, high-speed communication. Okay. So essentially, the fundamentally change the way we communicate. Okay. For those of you who do not know optical fiber, it's a thin, very thin glass, okay, a silicon glass. The core is about 10 micrometer, okay, but the standard one is about 0.1 millimeter, so it's 125 micrometer. Okay, because it's very thin, although it's glass, we can bend it easily. Okay, so the smallest band radius we probably can get it like in the millimeter kind of range. Okay. Because of the importance of optical fiber, the optical fiber have been installed almost everywhere. Okay, and people have estimated there's about 5 billion kilometers of installed optical fiber worldwide. Okay, so not only for the so-called terrestrial fiber. Okay, so typically the terrestrial fiber is that you use multiple wavelengths. Then every 70 or 80 kilometer, you amplify with something called the optical amplifier. It typically is designed using erbium doped glass, okay, and so can amplify light. Then the distance typically will be from like a few tens of meters, typically to about a few thousands of kilometers. Okay. There's also a huge amount of fiber for the submarine communication. Okay, so this one is a pretty old map. I think this one was from Optical. I think Optical actually have merged with other companies already. Okay, so this one can actually go even longer. Okay, so the longest probably is about 10,000 kilometers. Okay, so to do this one is very challenging because you need to provide the power supply. Okay, so you need a high voltage power cable over 1,000 kilometers as well. Okay. So over the past number of years, I think 20, 30 years, we have been pushing the limit of optical communication system, okay, of a single fiber. Okay. I think my group actually, we also have done a lot of work in the area. Okay. So essentially, we know that any communication medium, okay, the capacity is limited by the Shannon theorem. Okay. So Shannon capacity is essentially stated is that if you have a given bandwidth, you have a given signal noise ratio, then the maximum capacity will be limited. Okay. So the bandwidth is limited by the transmission medium. Okay. For optical fiber, typically is about 4.3 terahertz. So if we are using the so-called C band, okay, but we can also increase it to further to the so-called C plus L band. So this one will give you about 11 terahertz. So it's a huge amount of bandwidth. Okay. And then the signal noise ratio obviously is decided by the transmission distance. Okay, because whenever you transmit, your signal becomes smaller. When your signal becomes smaller, you need to amplify it. Any amplification process will add some noise. So eventually, your signal noise ratio will become worse and worse. So then your capacity will be limited. Okay. So, but although we have a huge amount of bandwidth, okay, so to utilize the bandwidth, we cannot use a single channel to do it, because that one is obvious, because our electronics, the speed is limited. So we cannot use electronics to switch on off the light at like a terahertz range. Okay. It's very difficult. Okay. Because the highest speed now we probably can get it about 0.1 terahertz, that's 100 gigahertz. Okay. And so, but what we can do is that we can use a different color of light, a different wavelength. Okay. So essentially we use a single wavelength, then we use a multiple wavelength. We didn't quite care how fast they are separating apart, because we had a huge amount of capacity. Okay. But then with the increase of the capacity requirement, okay, then people try to pack them closer and closer to each other. Okay. So eventually, then we also have used all the complicated transmission schemes. We have used, I think people have started for communication in the past 40, 50 years. Okay. And so eventually, we are using not only initially we use the so-called intensity modulation direct detection. So that means we only switch off on and off the light to represent 1 and 0. Okay. But then in the past 10, 20 years, people try to use a more complicated scheme. So we try to, in addition to amplitude, we try to use a phase, we try to use polarization, then to further increase the capacity. Okay. Then we also use other advanced schemes like probabilistic shaping and other things to increase the capacity. Okay. So what we have done, okay, I think this one represented, it's probably not the highest capacity anymore, okay, but it's very close to the theoretical limit of a high capacity optical communication system. Okay, so you can see that this one represents a combination of amplitude and phase when we transmit the signal. Okay, so because in communication, essentially we want to use a certain combination for amplitude, phase, and polarization to represent the combination for ones and zeros. Okay. And so that one represents all the possible combinations we have designed. Okay. So eventually, what's the capacity we have done? I think this one have achieved almost 100 terabits per second on a single piece of fiber over almost 2,000 kilometers. Okay. People also try to expand it in the space dimension. Okay? So in addition, so the typical fiber, you have a single core. So people say that can we use a multiple core, or can we use a multiple so-called mode? Okay? So the two-dimensional distribution of an electromagnetic field. Okay? Then certainly people can do even better. So that one I think was done by NICT in Japan. I think they have done like 172 terabits over about 4,800 kilometers. Okay. So I think communication, the capacity, we have done a lot of work. Then recently, I think there's a strong interest of integrate this communication system with the so-called distributed sensing system. Okay. I think for many years, I think we actually have been trying to, because in addition to communication, we also use optical fiber for sensing. Okay. So you look at the piece of optical fiber. Okay, it's very much. So what's the main motivation for us to do it? Okay. So the first thing is that we have a huge amount of fibers deployed already. Okay. Can we use this for something else? Okay. So one good example was I think when I was working with a company, I think they had a huge amount of fiber on the oil pipelines for communication purpose. Okay. So they're thinking that can we actually use this fiber to detect the leaking of the pipe? Okay. Or some people try to steal the oil from the pipe. Okay. This one typically can be done. Why? Because whenever you disturb the fiber, let's say you have a piece of fiber, you just pull it a little bit, okay, then you change what? You change the phase. Okay? Because remember, the wavelength of light typically is about 1 micrometer, okay, and 1.5 micrometer. Okay? So that means if you pull a little bit, so you will change the phase. Okay? So you change the phase by in communication, we are constantly detecting the phase of light. Okay? So that means we will be able to detect what happened on the fiber. Okay? So another thing is that whenever we change the fiber, let's say we push it a bit. So initially the fiber is a perfect circular. Okay? So if it's no longer circular, like it becomes elliptical, then the two polarization, the propagation speed varies a little bit. So that's why it's called birefringence. Okay? So if there's any birefringence, then the fiber, the polarization property, because we use it for communication, so we can also detect it. Okay? So that means we can easily detect strain, we can easily detect pressure, we can also detect the temperature change, because if there's any temperature change, then the fiber will expand. And also if the reflect index will change a little bit. Okay? So that's the essentially why we can use the fiber for sensing. Okay? So another reason we try to integrate communication with distributed sensing is that on a single piece of fiber, there's a huge amount of data. Okay, so if anything happened to the fiber, okay, I think remember, I think when I was in Hong Kong, 1 year there was an earthquake near Taiwan, okay, and then the fiber was broken. Okay, then people have a problem with the internet, okay, because they no longer have the fiber connection. Okay, so and people also accidentally they actually dig the ground and break the fiber. Again, they will result in huge amount of data loss. Okay, so how we can have an early warning of anything happen to the fiber, let's say on offline digging, a vibration caused by strong wind and other things, then we can use this sensing, fiber sensing to detect it. Okay. So that actually shows a typical things we can see that this one is a typical, the so-called optical communication detecting algorithm, the sequence. Okay. So essentially, I think you detect the signal, then you need to have a complicated signal processing process to obtain the timing, the phase, the polarization, and you also need to correct any distortions caused by the channel, the so-called adaptive equalization. So that's commonly used in communication system. Okay. So as we said, any external disturbance to fiber will cause a variation of polarization, cause a changing phase. Okay, then which can easily be shown here. So that means when you change, then if there's any disturbance, then there's a variation in polarization. This is a Poincaré sphere, so which typically used to describe the evolution of polarization state, okay, using the so-called Stokes vectors. Okay. Apart from us, I think some early work was done by Google together with a group of scientists at Caltech. Okay, I think Google has a huge amount of fiber, okay, submarine cable. Okay, they have been detecting the signals. Okay, so then one thing they realize that, as we said, there's any disturbance, then you change the phase, you change the polarization. Okay, so one thing which will affect the fiber in submarine environment, because submarine essentially is a very quiet environment, because you're not disturbed by many things, okay, because it's isolated. The electromagnetic wave cannot propagate inside the water, and the only thing that can propagate over long distance is the acoustic wave. Okay, so one thing is acoustic wave is the earthquake. Okay, so if an earthquake, then obviously your fiber will be disturbed. Okay, so they say that so they think they have been measuring the variation for phase and polarization all the time. Okay, so they think, can we use this one? Then we compare with the people who have been monitoring the earthquake activities, and see if there's any, correlation. Okay, I think so. They contacted a professor at Caltech who had been monitoring the earthquake activity for many years, and he actually say that they have a good agreement. So that means essentially you have a huge amount of essentially it's a very large long interferometer. Okay, so you can use. I think a lot of people know that LEGO for the gravitational wave detection. So that's essentially using interferometer. Okay, so that's why it's the same. Okay, so very sensitive. Okay, so they have done that work. Okay, but one problem with that one is that it's a long interferometer. So you cannot have the location information. Okay? Yeah, because you know something happened, okay? But you don't know the location. Okay? So one simplest way to have location information is to that's what we have did is that because typically in communication you have fiber in both directions. So the transmission in that direction, then the signal coming back. Okay. But if we take the signal loop back information, okay, so whenever there is any disturbance, it will act on the fiber twice, okay, in this direction, in other direction, okay. So if you detect the phase change here, then also the phase change here, then eventually if you do a correlation, then the timing delay essentially will tell you the distance. Okay. So that's actually what we did. Okay, I think we use about I think about 1,200 kilometer fiber, and so we apply some disturbance to the fiber using the PDT. Okay, so you can say that there's two phase changes. Okay, so if you do a correlation, then eventually you will be able to locate the disturbance, okay, and over a length of 600 kilometers. Okay. But certainly, one thing you probably realize that that one is good for high-speed detection. So that means tens of kilohertz, you can easily detect it. Kilohertz, good. But then very low frequency, then the thing may be affected. Okay. I think the reason is that the low frequency is always difficult to detect because you essentially the interferometer, so you need your light source to be extremely stable, okay, for the low frequency signal detection. Okay. So that work actually has been further extended by the NEC USA. So they actually have used communication channels. Okay. I think the deployed the fiber, then you actually can carry all the data information. Okay. But if you do a synchronization on both sides, then you can correlate the signal in both directions. Then again, you can detect the location. Okay. So the scheme actually has been used. We have also applied the system in one of the deployed fiber in Hong Kong. Okay. So the fiber itself is almost about 100 kilometers. Okay. So it's the fiber has been buried underground for many years. I think eventually I think it's donated to us by one of the data center providers and the Hong Kong Telecom. Okay, so we have used it for many experiments. Okay, I think so you can see that again. I think you can detect some of the disturbance and so on. Okay, so using a single fiber for sensing, I mean, it's pretty good. But then we see that we can also use it to have a certain kind of location information. But the main problem is that at very high, low speed, low frequency, we have a problem, and also the location information. Essentially, especially for low frequency, the spatial resolution is not very good. So we typically have a spatial resolution of let's say 50 meters or 100 meters, okay, which is not good enough. But for certain information, you really need a very precise localization. Okay. Let's say you have a water pipe, okay, underground. You want to locate the leaking. So let's say if it's 10 meters, you will not be able to dig up a 10-meter hole to repair the pipe. Okay. So you really want to have like a 1 meter or even less. Okay. So that one can be done using something very similar to LiDAR, because now people use the LiDAR for self-driving cars. Okay. And so that's one what we can do is that if we can have a back scattering, then it will provide us with location information. Okay. So people actually have been using it for distributed sensing for many different things. Okay. I think if we use a Raman, we can have a distributed sensing for temperature. Okay. So people can easily detect like 1 degree variation over 10 kilometers or even longer. Okay. And if we use a Bruin scattering, then we can use it to detect the variation in strength and the temperature. Okay. Then we can also use a relay backscattering. Then we can use it to detect some dynamic phenomena such as a vibration, acoustic wave, and so on. Okay. So way to do it is very simple. The easiest one is to use a time domain technique. Okay, so you send a pulse. Okay, so let's say for relay scattering, so the light will be coming back because inside the glass there's a random molecular arrangement. Okay, so the light will be scattered back. Okay. So the scattered back signal, if we detect it, then we have the location information. So the time and is corresponding to the distance. So very much like LiDAR. Okay. You can use a time domain technique. You can also use a frequency domain technique. So you sweep the frequency, then you can also obtain the kind of the location information. Okay. So that's actually what we typically do. Let's say you use a laser, you send the pulse to the fiber. So the fiber can be tens of kilometers in length or even up to 100 kilometers. Okay. Then you detect the signal coming back. Then the location is essentially decided by the time. Okay. Because c is the speed of light. N is the reflecting index of glass, typically it's about 1.5. Okay, so that means the light propagates inside the fiber is typically 2 times 10 to the power 8 meters per second. Okay. So one important application is to detect like acoustic wave, or the vibration of optical fiber. Okay. So how can we use it to detect acoustic vibration? Okay. So let's say we send the light. Okay. So let's say we send the light, which is so-called incoherent light. Okay. Then the light coming back to us will only reflect the power at a particular location, okay. The intensity. But if we use a coherent light, the inside the pulse, the light will interfere with each other. Okay, so any interference pattern will be random. Okay, so the randomness is completely decided by the fiber. Okay, so what kind of a random pattern you have is actually decided. So each individual piece of fiber will generate very different interference pattern. So although it is random, but the important thing is that it is fixed. Okay. So the randomness is decided when you draw the fiber. So people actually have used it, the fiber for as a certain kind of like a security device. So if we take that piece of fiber, clearly it will be different from another piece of fiber if we measure the interference pattern. Okay. So for this way, then we can actually use it for vibration testing. So how do we do it? Okay. So let's say we send a pulse. So the duration corresponding to the length of the fiber. Okay. So the longer the fiber, then the larger will be the duration. Okay. Because we can only send one pulse. When it comes back, say we send another pulse. Okay. So we generate this random pattern. Okay. If there's no disturbance to the fiber, this random pattern will remain unchanged. Okay. But if there's any disturbance at a particular location, then at this particular location, the interference pattern will change. Okay. So if we compare this measurement with another measurement, then if we compare it, then we know that there's something happened, okay, at that particular location. Okay. So that one can be done using either the so-called direct detection. Direct detection is that we use a photodiode, we only detect the power. Okay. Then the power detection essentially, if some people know photodiode, is a so-called square law detector. Okay. But if you square it, it's no longer a linear relationship. Okay. But we can also detect the phase directly, although the system is more complicated, but you can see that you can actually recover the signal almost the same as what you have sent. Okay, so we use a sine wave, so you can see that if you coherent detection, then we will be able to recover sine wave. If the direct detection, it will be distorted sine wave. Okay. So you can also improve it using some technique which is very similar to the people using LiDAR, called the frequency FMCW LiDAR. So essentially, you chirp the pulse, okay, then at the receiver side, they use a match filter, you compress it back, okay, so you can have a good spatial resolution, because the spatial resolution is decided by the pulse rate. Okay. So that's how you do it. Okay. So okay, so we can say that then we can use this one, then we can combine it with our communication signals. Okay, so that means we can use a fiber purely for sensing purpose. Okay, but then you will waste the resources, because you deploy the fiber, you still want it to be used to carry communication signals. Okay, so you want to add something which does not affect the communication signal, but at the same time, you will add this sensing capability. Okay. So if you see that one possible way that typically in the communication channels, okay, I think I will show you. In the communication signal, you typically have the so-called header sequence. Okay, the header sequence is for you to do the to go this pilot symbols for synchronization, for performance monitoring, convergence of equalizer. So they find the speed typically is lower. So that means lower speed communication typically you will be more tolerant to noise. Okay, and so that's why the so-called payload is our communication data. Okay, so what we did is that we add this FMCW signal onto the header. Okay, so because if you use the FMCW, then the power will not be very high. Okay, then if you compress it back, then you have a higher power than narrower pulse. Okay. So what we did, and now in order to separate it further, so we actually have put the sensing signal at right at the edge of the communication signal. Okay, and then another thing we have improved was we can add different frequency chirp, okay, at the different frequencies, okay, to each of the frames, okay, because they are at a different frequency. So as a receiver, we can separate them. Remember, previously, we can only send a single pulse at a round trip time, okay? And then this one will affect the signal detection quality. Okay? But if we can send multiple pulses, then we separate in frequency domain, then we can enhance the signal detection quality. Okay? Eventually, I think I'll skip some of the details. Okay, I think that's some of the experimental work. I think so. Essentially, I think what we did is that we actually have done. It's not too long. I think about 10 kilometers, but we can have a sensing resolution about the 0.5 meters. Okay. So essentially, you actually have a detection like a sensing array. Okay. The good thing is that you can have the array detection is that you can, let's say if you have acoustic wave, okay, so you can detect many of them because they are synchronized, so you can add them up coherently. So that means it's a very, very sensitive detection. Another thing is if you have a sensing array, then you can actually locate the information, the direction of the arrival, like of acoustic wave. Okay, so the many things can be done. Okay, so that is about 10 kilometer sensing with 0.5 meters resolution. So you can see that we can actually faithfully recover a good sine wave. Okay. I think I'll skip some of the detail. Okay. So that kind of system can be used for many things. I think that one was done by I think Professor Li Daohui in Yangsan University. I think last year I was actually spent the whole year there. Okay, so they actually been using this fiber for monitoring the bridge. So that one is one of the longest bridge in the world, connecting Macau and Hong Kong and Zhuhai. Okay. So because they have the communication cable underneath the bridge already, so you can actually see that you can use that one for monitoring the bridge itself. So you can see all the trains from Hong Kong to Zhuhai and Zhuhai to Hong Kong in different directions. So there's an earthquake, and anything happened at a particular location, then you can also see it. Okay. Then later, I think a piece of fiber, they also have the communication fiber between Zhuhai and one of the islands. Okay. So you can say that you can actually use it for many things. Okay. I think so that's why it's for earthquake detection. So you can detect about 1.4 Richter scale kind of earthquake, which is a very, very small earthquake. Another thing is that you can actually see the movement of ships. Okay. Yeah, because when there's a movement of ship on the surface of water, it actually disturbs the optical fiber. Okay. You can actually see the movement of ships. Okay. And remember, we actually had a piece of fiber connecting different parts of Hong Kong. Okay. Then my university is actually next to this so-called Cross Harbor Tunnel. Okay. So the Cross Harbor Tunnel is actually connecting Hong Kong. Actually, have three parts. Hong Kong itself is an island. Okay. Then the Kowloon is a peninsula. Then after Kowloon is a new territory. New territory is bordering Shenzhen. Okay, so next to Shenzhen. And so it's one of the busiest tunnel. Okay, I think it's probably less than Lincoln Tunnel of New York, but it's actually a lot of vehicles. Okay, I think it was more than 100,000 kind of vehicles per day. Okay, and then we will try to see that if we can use it to monitor the movement of cars and so on. Okay, and because the fiber is actually on all different parts of Hong Kong Island. Okay, so if I use it, then we can combine with I think this study was done in collaboration with the people study traffic engineering in Hong Kong. Okay. So we can say that in order to further enhance the performance of the system, then we use two fiber in the same cable. And so then we, because the different fiber actually, they are affected differently by the external environment. Okay, so we can further enhance the signal, okay, through the system. Okay. So essentially what we did is that we used the maximum ratio combination, okay, by detecting both signals, and we also have done some filtering, okay, because the heavy vehicle and light vehicles, they have a different kind of vibration signatures. Okay, so by doing this, so I think also skip. So you can actually see that you can have all the different small trucks, big trucks, and other things. Okay, I think I'll skip the signal processing part. Okay, and then because the fiber is actually under the underground, and then there's a subwave, I think, or in Hong Kong we call the MPRs. Okay, and they are also affecting this optical fiber. Okay, you can see that this periodic patch of patterns. Okay, so this one must be trends. Okay, so the trends actually have been affecting the optical fiber itself. Okay, and so the fiber, the sensing is pretty sensitive. Okay, because although it's not direct in contact with your train, even it can be quite further apart. But the thing is that acoustic wave actually typically can propagate, especially low frequency acoustic wave can propagate over quite a long distance. Okay? So that means it can easily be detected even your fiber is quite far from the location. Okay? But certainly, I think if it's affected by this one, it will also be affected by other things. So you need a certain kind of signal processing to obtain the kind of signal you want to detect. So then clearly, I think you use that one can detect train speed and inter-arrival time and stop durations, and so you can also based on the weight of the train, you can detect the passenger density and other things, information. Okay, so that one will give you the certain kind of information for the traffic planning, and without intruding into the privacy of people. Okay, because this one is very passive. Unlike you, I think you can use a camera to do it, but then I think the installation of camera, I think depend. I mean, you will not be able to cover all the areas. Another thing is that a lot of people worry about the privacy issues. Okay, when you have cameras. Okay. So essentially, I think I'll give you a very brief description, I think, of what in the optical fiber communication and the sensing community have been doing, okay, I think in the past few years, okay. So certainly the sensing will increase the value of your deployed fiber network, okay. I think what can be useful, I think really depends on the people's imagination. Okay, I think other work I haven't mentioned here that we have used the fiber sensor for the water leak detection of a water pipe, because whenever there's a water leak and the typical water pipe is a high pressure water pipe in order to send it over distance. Okay, so this water leak it generates quite a lot of acoustic waves. Okay, so we can use it for other things. Okay, I think other work we have done was we worked with the company on monitoring. Well, that one is purely sensor work. It's used to monitor the conveying belt of the coal mines. Okay, because whenever in the mine you get a coal, you need to send it out. Okay, then the conveyor belt typically may have a problem. Whenever there's a problem, the acoustic signature will change. Okay? So by detecting the variation of acoustic signature, then you should be able to see that what may happen to the conveying belt. Okay? And so I think many, apart from our work, I think a lot of a number of groups, I think internationally have been working the area in the past few years. Okay? I think for integrating communication and sensing in optics, I think it's only done in the past few years. I think although I have been doing communication and sensing in parallel, and also have used a communication technique to solve sensing problem. Okay, and then the integration work I think we planned many years ago. We did some initial work, but it's only I think this few years I think there's a strong interest in the community, okay, to do it. Okay, I think certainly there's a lot of work remain to be done. Okay, I think in the wireless community, there's also a lot of huge interest in communication and sensing. Okay, for example, people have used Wi-Fi to do sensing. Okay, so that one is easily understandable. Okay, let's say you have Wi-Fi signal in the room. Okay, so if you walk around, you affect the propagation of the electromagnetic wave. But in communication, we are typically constantly monitoring the variation of the channel. Okay, so if you know some variation, you know something happened. Okay, so you can use it for sensing. You can also use it to monitor the patient. Okay, I think the heartbeat and other things. Okay, but wireless channel is much more complicated because it's three-dimensional. So optical fiber is much easier because it's one-dimensional. Okay, I think so. As a result, I think it's much more sensitive as well. Okay, and also we can use it for much longer distance. Okay, and then other things I think my students actually been doing is that we are trying to integrate the two, okay, the wireless sensing and the fiber sensing, because in the future, okay, let's say 6G system, people actually try to generate the radio waves, okay, the microwaves, using some of the optical technique. Okay, so that means you can send the optical signal. Okay, you carry your optical data to optical sensing. You send it to the open space. Then you can also use it to do the wireless sensing. Okay, so then again, I think how to combine it is there's a lot of challenges. Okay. The other thing is that how we can use it for different applications. Then obviously, I think it depends on signal processing. I think my students also have used a lot of like a very simple AI technique. Okay, I think for any, if you want to detect a particular event, then obviously you need the AI to help to train the system. I think fiber essentially is a system that can collect huge amount of data, okay, because you have like tens of kilometers for fiber. If you have a spatial resolution of, let's say you have 10 kilometers, your spatial resolution 1 meter. So essentially you have 10,000 sensors, okay, and constantly monitoring the variation. Okay, so how to process it and how to get useful information from the data obviously is a challenge. Okay? So that's why we have been constantly trying to work with those people working in the other area like the AI area and the data, big data, whatever, and try to make whatever information we obtain useful for the society. Okay, and okay, I think finally, I think because I'm involved in two of the journals, I think we'll just do a little bit of advertising. I think so. That's why the photonic research, I think, is typically, I think, is a pretty good journal on the application for photonic technique and some of the fundamental techniques as well. Okay, and another journal I'm involved is Science China Information Science. I think it's more comprehensive. I think it involves people working optical communication, wireless communication, and even like AI and other things, anything related to information. Okay, I think so if you have a good work, I think you're encouraged, especially so students, you're encouraged to submit your papers to this journal. Okay, thank you for your attention.
Thank you very much for a very interesting talk. Are there any questions?
Thank you very much for this brilliant talk. I want to know, in terms of the sensing part of the optical system, what's the most, beneficiary add-on to it that can be more, for example, more informative of, for example, the Earth and related applications?
Okay. Yeah, thank you. Yeah, I think people actually have used it for to study what's it called the structure of the Earth. Okay, because like a different layer of different rocks and different Earth. Okay, so one way to understand it is to send the acoustic wave to it. Okay, and so for different kind of Earth, different rocks, I think the acoustic signature will be different. Okay, so it depends on how the signal are reflected back, then you know the Earth's the structure and so on. Okay, so that's I think that actually most I think the most sensitive one is to use the so-called distributed acoustic sensing. Okay, because distributed acoustic sensing is very sensitive to acoustic waves. But then let's say it also is typically about tens of kilometer, 10 kilometer, 40. I think currently we can easily do like 40 kilometers, okay, and then with the spatial resolution for 1 meter to about 5 meters, okay. So then you can have multiple sensors, okay. So you can either add them uncoherently, so you have a much sensitive signal, okay. And the other thing, as I said, is that you have a sensor array, then you can also have a location information. Okay, so you can have let's say you have 2 fibers, okay, and 3 fibers, you can also do the localization of where is the center of acoustic wave.
Other questions? So I had a question real quick, actually. Do you know, has anybody ever used, for example, say, GPS signals or like other signals that go out to like satellites in space to try to do something similar to this to monitor like the ionosphere or other parts of the Earth's atmosphere?
For the satellite, okay.
Yeah,
I think
like signals like from the ground up to a satellite, if they have to pass through the ionosphere and other portions of the Earth's atmosphere.
Yes and no. I think satellite, I think is good to do the imaging. Okay, but then if you try to do the sense acoustic wave, that obviously not very sensitive, okay, because the acoustic propagation needs air, and also it probably propagate very well in some of the rock structures and so on. Yeah, and water.
Okay, let's thank our speaker again.
Thank you.